All right, hello everybody. Today we are going to wrap up the first order differential equations, the circuits with just one capacitor or one inductor. And in the next lesson, we will be solving circuits with two capacitors and one capacitor and one inductor, or something like that. And those are going to require second order differential equations. But for right now, here are some more of the advanced topics. And I forgot to mention in the last video, if you haven't watched my first two introductory videos, which I should be able to link up above, please, I highly recommend watching them for your own sake so that you get to know how these things are working and you're not getting lost as I go through them. With that being said, let's go ahead and get going. So right here we have a circuit, and it's a classic op-amp, but we have a capacitor in the op-amp and we have a switch. And so, like normal in our transient analysis, we are going to start with step one, which is to find everything that is happening between negative infinity and 0. So we're going to go ahead and redraw the circuit, and I think I'm just going to copy and paste this. Remember, so the switch is open, so this entire branch is gone, and the switch is open and it's in this DC environment for a good while, so this capacitor is just nothing. Okay, it's just an open circuit. Now, we are going to perform a nodal analysis, and remember, in an op-amp, this is a separate node and this is a separate node, but they share the same voltage, and this one is being forced with 4 volts. So it's only logical that this branch will have 4 volts. So let's go ahead and solve for N2 to get in terms of V out. We have a plus, we have just a capacitor right here and no voltage. The same voltage across it is 4 up to V out. So we are just going to say 4 minus V out, I'm just going to say V0 over 10 is equal to 0, because we have nothing going out this way. This current right here is 0, so I'm not going to write it. Multiply both sides by 10, and we're going to see that V of 0 minus is equal to 4. And thankfully, this is a capacitor, so we are just going to have 0 minus is equal to V of 0 plus, which is equal to 4 volts. So that's the first portion. Now we're going to look at step 2, which is from 0 to infinity, and that is going to have the entire circuit activated. So this switch is going to close, and our capacitor becomes alive, and we still have a 4 volts right here. We're going to apply a nodal analysis. We're at node 2, and I'm going to call this node 2 because this is node 1. We're going to go ahead and just solve this like normal. 4 minus 8 over 2, and we have we have that one current right here, this one current right here, which is 0, one current here, and one current here. So we expect 4 terms. So I got 4 minus 8 over 2 plus 0 to account for this op-amp right here, plus 4 minus V out, plus, now this is the tricky part. So notice we are going from this voltage, which we know to be 4, to this voltage, which we don't know. And we have to cross this guy. So we have to, there's some voltage difference between here, right? There's a voltage difference from getting to here, and we have the current going this way. So we are just going to say V prime 4 minus V naught is equal to 0. And the thing about this is you don't actually need to know what the constant is. This could be an arbitrary constant. What we care about is this minus sign, and you'll see why. Remember to put your farads in. That's super, super important. There we go, that's better. So we've got V naught prime plus 200 E3, V naught plus 3.2 E6 equals 0. We're going to go ahead and solve this out. We're going to have a homogeneous equation. So V naught homogeneous is equal to K1 e to the negative 200 E3 T. And we're going to also have a particular solution. So V naught particular is equal to K2. And we're just going to plug it into this equation right here. 200 E3 is equal to K2. K2 is equal to negative 3.2 E6. And we're going to divide both sides, and we're going to get K2 is equal to negative 16. And when we combine this all together, we get V naught of T is equal to negative 16 plus K1 e to the negative 200 E3 T. And we did find our initial condition earlier. Our initial condition was just 4, so we're just going to say 4 is equal to negative 16 plus K1 because we put a 0 in here. And so K1 is equal to 20. And we get V naught of T is equal to 20 minus, 20 e to the negative 200 E3T minus 16. And that is our answer. So super simple, super easy. The only thing that you need to consider really is this the voltage across this capacitor right here, and then other than that it's the same thing. All right, so here is our last case, and this is our last one because it's a long one. We have actually a time varying battery. Thankfully it's just a constant voltage, not a sinusoid or some AC current. We have a 10 millifarad capacitor in the middle, and now for this, we're actually going to have 3 different scenarios rather than 2. We're going to have the negative infinity to 0, period. We're going to have the 0 to 2, period, and the 2 to infinity, period. So let's go ahead and get started. So step 1, that's just going to be the negative infinity to 0, period. And we're in a DC environment at this time, so our capacitor is just going to be open. We don't need it right there. And our battery is going to be non-existent also because the voltage is 0 at this portion. So, but it's not an open wire. That's the thing. It has 0 volts, so it's directly connected to ground. So you need to make sure that you can't just assume that everything that is a battery or some voltage is just going to be an open circuit, like how we normally think about it with the capacitor. So you got to think about it like that. Now, we actually have 2 unknown nodes. We have this V2 right here, and we have this V1 right here. And we want V1. I'm just going to call V of t V1 for simplicity's sake. And we're going to apply a nodal analysis. And look at this. It's just a basic nodal analysis. We're going to say N1 V1 minus 0 over 2 plus V1 minus V2 over 4 is equal to 0. And we're going to go ahead and simplify this out, multiply both sides by 4. And we're left with 3v1 minus v2. Now let's go ahead and solve for n2. And n2 is going to be v2 minus v1, and then the v2 to ground, and then we have a current coming out. So we'll get the current out of the way. v2 minus v1 over 4 plus v2 over 2 is equal to 0. We're going to multiply both sides by 4. We're going to get 8 plus v2 minus v1 plus v2, 2v2 is equal to 0. And simplified, we're going to get negative v1 plus 3v2 is equal to negative 8. We're going to plug this into a matrix, and then using a calculator, you can solve it. And thankfully, we get some really pretty numbers here. We get v1 is equal to negative 1, and v2 is equal to negative 3. Now, remember that we are in the v of 0 minus portion, so technically this is v of 0 minus 1, right, is equal to negative 1. We don't care about this because our capacitor, or the voltage that we want, is not v2. We only care about v1. We only have to find v2 was a byproduct, essentially. Okay, so this is our first puzzle piece, part of the puzzle. And so that's going to say that during this time, we have v1 as being negative 1 volt, right, during that time. Now, we are going to have a change, and we are going to have step 2. I'll write this right here. Now, step 2 is going to be from 0 to 2, and basically everything is active now. The capacitor is active. This voltage right here is now 4 because of this, the time graph is telling us that it's 4 volts right there. So once again, we're going to do another nodal analysis. We've got a V1 right here and a V2 right here. So let's go ahead and solve the nodal analysis at N1, node 1. And we're going to have V1 minus 4 this time instead of to ground, divided by 2, plus V1 minus V2 over 4, and then plus V1 prime, okay? It's equal to 0. And once again, I'm about to forget the millifarads. V1 prime is equal to 0. Okay. I'm going to go ahead and simplify this guy down, multiply both sides by 4. And now we're going to go ahead and solve for N2. N2 is just going to be, so we've got V2, basically the same thing. So I'm just going to write it down for formality's sake, because what we're going to do is, once we get down to the simplified version, we don't want this here. We don't want this here because we have a differential in the V1 and we don't have V2 there, and so we want to eliminate it. So we're going to have V2 is equal to V1 minus 8 over 3 by solving this out for V2. And we're going to go ahead and plug this back into this equation. And so this right here is going to be V1 minus 8 over 3 minus 8. Don't forget that 8. Multiply everything by 3. So we got 120e negative 3 V1 prime plus, what is that, 9 V1 minus V1. So that's just 8 V1 right here. Plus 8 minus 24 is equal to 0. Subtract these guys right here and then divide out by 120 e negative 3, and our resulting equation is going to be V1 prime plus 200 over 3. V1 is equal to 400 over 3. All right? And as you can see here, this is a non-homogeneous equation. So we're going to have a V homogeneous, we're going to have a V1 homogeneous, which is simply K1 e to the negative 200 over 3t. And V1 particular is going to be equal to K2. We're going to plug this bad boy in, get K2, and then these guys cancel out, the thirds and the thirds cancel out. 400 divided by 200 is just 2. And then we are going to get V1 of t is equal to 2 plus K1 e to the negative 200 over 3t. And remember what our initial condition was. It was V1 0 minus equals V1 0 plus is equal to negative 1 volt, I believe. And so we are going to plug that in, 2 plus K1, and our resulting equation is V1 of t is equal to 2 minus K1 is equal to negative 3 minus 3e to the negative 200 over 3t. Just like that. This is one part of our solution. This is one part of our solution because we're asked to graph for all time. So we've successfully found V1 in this little portion of time, and that is 2 minus 3e to the negative 200 over 3t. One more to go. So what's going to happen in this step 3 is we have no more of this battery. This battery has become 0. However, this battery is now 0, but also this capacitor is on because it's in the transient phase, right? We just changed what's happening to this circuit again. So it's not yet an open circuit. So we still have to consider this capacitor. So we're going to go ahead and make our nodal equation. We have node 1 right here and node 2. And mind you, V2 still has not been affected by this right here. So instead of actually writing N2 back out again, we can just put our little dependency right here. And we're going to need that once again. So V1 over 2 this time instead of any minuses, plus V1 minus V2 over 4 plus, let me move this guy over a little bit, 10e negative 3 V1 prime is equal to 0. Multiply both sides by 4. And now I'm not going to go ahead and write this V2. I'm going to write this V2 right here. So V1 minus 8 over 3 is equal to 0. Multiply both sides by 3. 120e negative 3 V1 prime. And then this is just going to be 9 minus 1, which is plus 8 V1. And plus 8 is equal to 0. Alright, and once we've simplified this all out, we're going to get V1 prime plus 200 thirds V1 plus 200 thirds equals 0. Once again, it is a non-homogeneous equation, and we will have a homogeneous solution, which is just the same thing. K1 is e to the negative 200 over 3t. And V1p is equal to K2. Plug in this K2, this guy cancels, and we have a negative 1 right here. K2 is equal to negative 1 because plug in K2, subtract this side, they're the same. We'll get negative 1. And let's go ahead and plug it in. V1 of t is equal to negative 1 plus K1 e to the negative 200 over 3t. And we are going to plug in what initial condition? How are we going to find the initial condition from here? Well, we can go ahead and look at this equation right here. This equation will tell us what we are going to need, or what we are starting with, right, to find our initial condition. So we are going to have to plug in a time of 2 seconds because this transition happens at 2 seconds. And thankfully, this right here is already a pretty huge number relative to this whole equation. And so this effectively cancels out to being 0 because even if you had this 3, that's like e to the 66th, right? Or something like that. And then multiplied by 2, so e to the 120th, which is a humongous number. And so we will just get 2 volts. So that would be our V1 of 2 minus, right? Because we are looking at just on the verge of changing, right? So we were looking at on the verge of changing from here. Now we're looking at on the verge of changing from here. So we are going to go ahead and plug in this 2, and I'm going to say 2 is equal to -1 plus k1 e to the 0. So k1 is equal to 3, and we've got v of t is equal to -1 plus 3e to the -200 over 3. And I made an engineering shortcut. So this works if I said that 2 was equal to 0, okay? If I said that we were measuring from 0. However, if we want to be mathematically correct, we are actually going to have an offset of t minus 2, right? So that earlier we were just pretending that this was 0. The reality of the situation was that we had t minus 2. So if you're a math person and you were watching me go through this, I really hope that you stuck around because I was going to address this. But generally, for our purposes, that's not circuits, that's math. It doesn't matter as long as you know about it and you know that it exists. So this is the mathematically correct version, and so we have effectively found this portion right here. Now, for visual people, and it's just a good thing to know, we are going to go ahead and graph this. So first of all, I know that we have a negative value, so I'm going to have this y-axis be the voltage, and this t be time, the x-axis be time. I'm going to go ahead and grab, well, I'll just go ahead and write them. We'll go ahead and write our entire piecewise function, because that's what this is. It's a piecewise function. And we know that from -infinity to 0, our voltage is just -1 volt, okay? And then in our transition period from 0 to 2, we know that the equation that represents the voltage is this. And then from there, we know that the equation that is represented is this. From 2 to infinity, okay? So let's go ahead and draw our graph. So I'm going to make this a little longer. So we have 2 right here, t equals 2. That's important. And we have, of course, t equals 0 right here. And we have from infinity, from negative infinity, we are at -1 volt, okay? And then up until t equals 2, right, we are going to stop at 2. So we are going to have asymptotic behavior at t equals 2, and we are going to go up like, we are going to go up like this, right? And then we're going to taper down, you know. But at t equals 2, someone flipped the switch on our voltage source, and now we have nothing. We have no voltage. Someone completely cut our power off. And we are going to start, you see, if I plug in a 0 right here, I have -1 plus 3, and that equals 2, right? So we are starting where we left off from here, because if I say 2, and then this was an infinity right here, a negative infinity, then we would be starting at -1, right? Because e to the 0 is 1, and etc., etc. And so, but if I, yeah, you get what I'm saying. And so we have this curve up to this asymptote, and then our equation shifts to this guy right here, and you can see that after a really long time, this whole term is going to just go away, and because that's going to be 0, and we are just going to be left with -1. So we are going to go back down to our base voltage, like so. And that's basically it for first order differential equations, that is with capacitors and inductors. Capacitors and inductors are represented with first order differential equations, one capacitor and one inductor, and they are considered transient because this is the phase that's going to happen between basically a change in the DC environment. Now, next video is going to be about second order differential equations. We're going to see what it's like to have a capacitor and an inductor in a circuit with resistors. So we'll be doing RLC circuits, and those are going to require second order differential equations if you're looking at them from a transient viewpoint. All right, that's it.